so far all of our wave descriptions has applied to any kind of wave. Now we're going to focus in a little bit more specifically for a wave on a string. We know that from experience, waves depend on the strings themselves. So if you think about a guitar, all of the strings sound different. So the wave on the string must depend on the string. Here's a really simple way to show it. I grabbed two rubber bands. This one came off broccoli. I think this one came off asparagus. I'll stretch them out between my fingers. I don't know how good my iPad microphone is, but they sound different. So the waves on these two rubber bands, and the two rubber bands are different, the waves are different. So what we're going to do next is let's see how do we find the speed of a wave on a string. So we're sticking with traveling waves, and the part we're going to stay with, and we mentioned this a little bit at the end of the last lecture, we're going to stick with linear waves. Okay? The treatment for nonlinear waves gets a lot more complicated, and of course we want to start at the beginning, so we'll start with linear waves. If you find this pretty neat and you also like math a lot, you might be interested in a nonlinear dynamics course at some point. You might find that kind of interesting. And what a linear wave means is that the amplitude of the wave is a lot smaller than the wavelength. Normally I don't draw them that way because the waves are hard to look at. So normally I exaggerate the picture, but we are talking about cases where the wavelength is much bigger than the amplitude. And you'll see that in all of the examples that we do. The amplitude is small compared to the wavelength. So where we'll start is let's look at this wave pulse on a string, and let's pick a little small piece of that wave. So I'm just going to grab this little bit of the string. So there's a small segment. Of the string. Of the string. Our wave, of course, is a curve. One benefit to picking a small segment of that string is we can pick a small enough segment so that it's approximately circular. So we'll take this little small segment. I want to be able to draw some forces and things on that. So the next thing I want to do is just zoom in my picture. So I'm going to just take my camera, zoom in on this, and my little segment of string looks like this over here. So we'll say we're going to zoom in. So now, this little segment of string, what can we say about this guy? Well, our little segment of string has a certain length. The length reaches from here to here. If you're thinking about the fact that this is a curve and is that important with the length, it certainly is going to be important. So my small segment has length. Maybe this is not going to be my day. I spelled length wrong. Has length L. And it's under an amount of tension which we'll call T. T, and let's put an S on it for T of the string. So we know that the tension in a string is going to be uniform the whole length of the string, and we know that we only pull with a tension, so a tension tightens it. So on this end of the string, the tension pulls along its length. We'll label it TS. On this side, it pulls, comes straight out from its end, and that's TS here as well. Tensions are forces, so they are vectors. Because they're vectors, we'd like to fill in some things about vectors. So let's break our tension on the string into components. So we'll put in an X and Y coordinate system. I think I can squeeze that in right about here. So we'll take positive X to the right, positive Y to be up. So on this side, the X component of tension, and I'll draw that with a dotted line. The X component of tension points to the left. Try and get it to right length. So there's my T on the string in the X direction. The Y component points down. t and the string and the y. Over on this side, the x component points to the right and the y component points down. Okay, so there's our tension, there's our components of tension, the length of the string is L, and our coordinate system is written down. Where are we going to go from here? Well, after we draw forces and their components, our next step is that we apply Newton's second law. So if we write down Newton's second law, and let's look at the sum of the forces in the x direction on this guy. We've got a tx to the left, so the sum of the forces in the x direction is a tx to the left, so minus tx, and a tx to the right, plus tx, equals 0. That tells us that the x component of acceleration of this string is 0. And that makes sense because that bit of string doesn't go anywhere horizontally. Okay, so that's a logical result. We're okay with that one. There's no left or right motion of that string. There's our x component done. Next, let's do the y component. The sum of the forces in the y direction. We have a minus ty here, minus because it points down, a minus ty here, equals mass times acceleration. The acceleration will point down, so that's also negative. So next thing we can do is everything here is negative, so we can multiply both sides by minus 1, make everything positive. We have 2 of these ty's, so 2 times ty equals mass times acceleration in the y, where this m is the mass of this little bit of string. Okay, so we have a y component of a vector. We know to find our components we need to apply our trigonometry, sines and cosines. Let's label this angle right here theta. So then our y component is opposite our angle theta, so ty is t times sine theta. So 2 times the tension in the string times sine theta equals mass times acceleration in the y. Okay, where are we going to go from here? How are we going to deal with sine theta? Because where we're trying to get with this treatment is to find an expression for the speed of the wave. And the angle is not something we know, so what can we do about this angle? Well, let's go back to the picture. If this angle is theta, okay, then right here, between tx and ty, that's a right angle. So this angle in right here, that must be 90 minus theta. And then from here to here, well, why don't we go ahead and draw out that line? I can draw a radius of this circle. So there's a line that comes from the end of the string right to the center of where this would be if we completed the circle. Can also draw a radius that goes up to the middle of the string. This one right here, that angle would also have to be theta. Not sure I can quite get it in there. Theta. Okay, between tx and ty, that's 90. If this angle is theta, then this one is 90 minus theta. Ts is tangent to our piece of rope because it pulls along the rope. The radius is perpendicular to the rope, so these two guys are a 90-degree angle. If this is 90 minus theta, then this one has to be theta. Okay, this is a vertical and this is a vertical, so this angle is also theta. So there are all the places where we've written down theta. Now the next thing we can think about here is that the amplitude of this wave is a lot smaller than the wavelength. That means that the curve is very shallow compared to its length. So this is not a sharp curve because the amplitude of that wave is very small. So if A is much less than the wavelength, then it means that theta is small. If theta is small, then sine of theta is about equal to theta. Now important here is that this is in radians only. If you wanted to try this out for yourself, you certainly could. Grab your calculator, try doing the sine of 0.1, sine of 0.2, sine of 0.3. You'll see that it equals to approximately 0.1, 0.2, 0.3. Okay, so this is simplifying a bit. Instead of sine theta, we can write theta, as long as we're dealing with linear waves. But is there anything else we could say about theta? Let's go back to the fact that this L is a length along the curve. That makes L an arc length. So right here to here, that's L. That's an arc length. Now, you may or may not remember from a high school geometry class that an arc length is the radius times the angle. So this arc length L is the radius of whatever this circle is times the angle from here to here. Okay, so that whole angle. The angle on this side is theta. The angle on this side is also theta. So that arc length is r times 2 theta. So that gives us something we can put in for our theta. So theta is equal to L divided by 2 times r. So there's something we can do with this side. Now let's come back to this acceleration. This is a small segment of string. It's only moving vertically because there's no motion in the x direction. There's no left or right acceleration. And it's circular, so it's moving vertically, it's circular. That means we're talking about circular motion here. What do we know about its circular motion? We know that for circular motion, the acceleration is the speed squared divided by the radius. Okay, now this is really coming together. We've got a tension, we've got something about the physical parameters of the wire, and we've got the speed of the wave. Let's put all this together. So 2 times Ts times sine theta, which is approximately equal to theta, which is equal to L over 2r. So 2 times Ts times L over 2r equals m times v squared over r. What can we do with this equation? Well, got a 2 on top and bottom, they cancel. Got an r on bottom of both sides, so you can multiply both sides by r, and we're left with this. This gives us that v squared is equal to the tension times the length divided by the mass. So let's solve this for the speed of the wave on the string. So v, the speed of the wave on the string under tension Ts, is the square root of Ts over mass over length. Now we can leave it like this, but this m over L, we normally do something with that. And the thing that we do is we define a new quantity called linear mass density. So to clue this up, we normally define linear mass density. Linear mass density has a symbol of mu. That's the Greek letter mu. It's like a U with 2 little curly tails on it. That's mass of the string divided by the length of the string. So sometimes that's also called mass per unit length. And the units of that guy would be units of mass divided by units of length. So typically kilograms per meter. So then to finish up our equation for the speed of the wave on a string under tension Ts, V is the square root of the tension divided by the mass per unit length. So there's the equation that we'll use to find speed of waves when we know the tension on the string. And the last little note that I'll put in here with a star is that we often use this with V equals F lambda. We won't do any examples of that right now, but this is going to come back when we get to chapter 17, so I'll poke it in here now so that you'll have that fresh in your memory as you do a review. Okay, next video we'll do some examples.